Hi, welcome back. In this lecture I want to talk about operation on complex valued vectors or arrays. So we're going to use this one, we're doing calculation, so I want to go through more formal definition. So we're going to talk about inner product or dot product, the norm of a complex number, and the distance. So these two concepts can be derived by the definition of this inner product. But let's start with the first slides. So what is the motivation for doing this? Well, the motivation for introducing, for instance, the inner product is really that we want to have a mean to compare two complex vectors. So in this particular lecture, we're going to look at the complex vector space, so the space formed by all complex values vectors, and we want to have an additional structure that is given by operation we can do on this space. Why is important for this course? Well, it's important because it turns out that the state of a quantum system will be a vector in a complex vector space. We saw, for instance, in the previous lectures that we have a qubit, and we're going to use a column vector with C0 and C1 to represent the probability. A need will arise when doing quantum computing to compare different states of the quantum system. So there is a need to compare corresponding vectors or measure one vector against another in a vector space. And that's why in this lecture we are going to introduce this operation. The first and most important operation I'm going to introduce in this lecture is the so-called inner, but you also find in the literature a dot product operation on two vectors. So if we have two vectors, v1 and v2, we can take the inner product. So we use this notation like this one, often like just a comma, and then we take v1, that is the forward first vector, and then on the other side of these triangle brackets we have a v2. So v1 can be, for instance, a column vector, and then v2 is going to be also a column vector with the same number of elements. So this is just a fancy notation to do like a inner product or dot product. So we have a two vector, in this case v1, with elements 5, 3, minus 7, and then the second vector v2 with elements 6, 2, and 0. So how we calculate the inner product? Well, we basically multiply element by element and then we sum it up. So for instance, if we have two vectors in the general form row 0, row 1, and row 3, we can take the inner product, that is also can be done in this with the star, but basically multiplying element by element and then sum it up, the results of this multiplication. So in this case, I use elements from real numbers, but we can do exactly the same thing using complex number. So an inner product in a complex vector space is a binary operation that accepts two vectors as input and outputs a complex or a real number. So keep in mind we started from these two vectors, right, v1 and v2. We apply inner product and then we multiply element by element and then sum it up like here, and we obtain one single real or complex one real number. So we start from two vectors and then we output just one element. So the inner product, also called dot product, on a complex vector space is just a function, including this triangle bracket, going from this vector space to give an output that belongs to the complex number, either real or complex. We can go through a formal definition of the inner product. So we can define inner product definition as we want, as far the inner product satisfies these four properties. So it must be non-degenerate, this is the property here. It might be respect the addition that is expressed here. We also need to respect the so-called the scalar multiplication. So we have a scalar multiplication of the inner product, and then also this symmetry. So if you take the inner product of V1 with V2, this is also equal to the inner product of V2 with V1. So as far our operation can respect these properties, then we have an inner product. A complex inner product space is a complex vector space along with the inner product. So we start with our space that consists of a complex vector that we're going to use for modeling quantum computation and quantum state, and we add an operation that is the inner product that satisfies the operation we saw in the previous slide. Once we defined the inner product, also we can define the so-called norm operation. So given just one vector, either real or complex, for every complex inner product space, so we have already this inner product, we can define a norm or length that is a function that represent with the two bars. So we saw these two bars before. We go from a complex vector to a real value number. So we saw this before. So the norm or a vector can be defined by taking the inner product of the vector with its cells and then take the square root of this number. Let's look at an example of the norm. So remember what we need to do. We use the inner product of this vector with itself, and then we take the square root. So we take the inner product, the square root, which is just another step, and we see that we multiply element by element, and then we sum it up here, and we take the square root, and the final result is 7. Also, properties must respect some properties. Norm is non-degenerate. Must obey to this very important triangle inequality. That is the norm of the sum of two vectors, v plus w, must be less or equal than the norm of the sum of the norm of the two vectors that we see here. And this is called triangle inequality. And finally, it needs to respect the scalar multiplication. But why I said that this property is particularly important? Well, this inequality is an inequality that we actually leverage in the previous lecture when I talk about the interesting effect the usage of complex number has in quantum computing. So if you remember, in the previous lecture, I talked about this property here. This is basically equivalent to the triangle inequality. So it's built in the definition of inner product, is built in the definition inner product applied to complex number. And we saw before that is also given by interference phenomenon. So finally, let's look at the last function that we can apply to a vector, either real value or complex value. So for every complex inner product, we can define also distance function between two vectors. The distance function between two vectors is defined as follows. So we take a norm, and then we take the difference of the two vectors. So just a definition that we can calculate from the norm product. It's probably no surprise to you at this point that we also need to satisfy a number of properties. Distance must be non-degenerate. It must satisfy the triangle inequality we had discussed briefly in the previous slides, and it must be also symmetric. So the distance between the first vector and the other vector must be equal to the distance of the other vector with the first vector. I want also to introduce very quickly the idea of a Cauchy sequence within an inner product space V that also has associated norm and distance function with this inner product. So we call a Cauchy sequence a sequence of vectors, so v0, v1, v2, dot, dot, dot. So we call it Cauchy sequence is for every epsilon greater than 0, there exists one n0 belonging to the integer number, such that for all m and n greater than n0, the distance we can find the two vectors for which the distance is less or equal to epsilon. So we introduce these concepts of Cauchy sequences within inner product space. We also call about complete Cauchy sequence when we have a Cauchy sequence of vector v0, v1, v2, and there exists a vector v tilde belonging to the vector space V, such that the limit between the limit of the norm of Vn minus V tilde is equal to 0. So the intuition behind this is that vectors, we have a vector space with an inner product, call it complete, if any sequence is basically accumulated somewhere converging to a point here. But why I introduce like a sequence of vector, I talk about Cauchy sequence, I talk about a complete. Well, the reason for that is that I want to give a formal definition of a Hilbert space. So whenever we deal with the quantum computer, you might already heard about Hilbert space, right? So you will hear over and over all the papers about the Hilbert space. So what is Hilbert space that we deal in quantum computer? Well, a Hilbert space is a complex, so we are going to deal with vectors and matrices that have a complex number, that have an associated inner product that is complete. So there is this accumulation point. So every inner product on a finite dimensional complex vector space is automatically complete, and therefore every finite dimensional complex vector space with an inner product is automatically Hilbert space. So most importantly, when doing quantum computing, we will deal always with Hilbert space. And therefore, I really wanted to introduce you, even though it's a little bit in a rush, the concepts of Hilbert space. So remember, we are dealing with the complex number, and then we have associated operation on this space. So this is the last slides of this lecture, and talk to you soon.